On the 29th of June 2022, something happened that had never happened before in recorded human history. It wasn't a storm, it wasn't an earthquake, it wasn't a volcanic eruption or a tsunami or any of the other catastrophic events that tend to dominate headlines and emergency broadcasts. It was something considerably quieter and considerably stranger than any of those things. It was something that almost nobody noticed, because it happened at a scale of precision so fine that it required atomic clocks to detect it. It happened below the threshold of human sensation. It happened to the most basic unit of your existence, the length of a day, and it went unnoticed by 8 billion people going about their lives. On June 29th, 2022, the Earth completed a full rotation in less time than it ever had before in the era of precise timekeeping. The planet spun faster than normal, not by much, not by seconds, not by fractions of a second in any perceptible sense, by 1.59 milliseconds, 1.59 thousandths of a second, the shortest day ever recorded. If you are tempted to shrug and move on from that number, I want to ask you to pause, because 1.59 milliseconds is not the story. The story is what scientists found when they went looking for why. The story is what they discovered when they started pulling on that single thread, that almost imperceptibly shorter day, and found a tangle of interconnected systems, each one influencing the others, each one changing in ways that are accelerating, each one pointing toward a planet that is quietly, steadily, measurably shifting beneath our feet in ways that most people have no idea are happening. The story is this: our planet is not the stable, reliable, predictable system that our everyday lives allow us to assume it is. It is a dynamic, layered, interacting machine of almost unimaginable complexity, and it is being pushed, pulled, and perturbed simultaneously by forces that range from the deepest iron depths of its core to the surface of its ice sheets, to the weight of the cities we have built and the groundwater we have pumped out of the ground. Every one of those perturbations feeds back into every other one, and the result, playing out in real time at the level of atomic clock precision, is a planet whose rotation, the fundamental rhythm of our days, is changing in ways that scientists are still working to fully understand. The inner core of the Earth, and the solid iron sphere at the very centre of our planet, roughly the size of the Moon, may have recently reversed its direction of rotation relative to the outer core surrounding it. That sentence alone deserves its own video, but we are going to cover it here because it is part of the same story. The inner core's rotation affects the length of our days. It influences the magnetic field that shields life on this planet from solar radiation. It matters in ways that extend far beyond the purely academic. 400 billion tons of ice are disappearing from Earth's polar regions and glaciers every single year. Not accumulating, disappearing, melting, carving into the ocean, becoming water and redistributing its mass around the planet. And when mass moves on a spinning object, the object's spin changes. This is the same physics that makes a figure skater spin faster when they pull their arms in toward their body. When Earth's ice melts and the water flows to the equator, the planet's mass distribution shifts and the planet's rotation responds. We are, collectively and mostly unknowingly, adjusting the spin of our planet through our greenhouse gas emissions. And then there is the most unexpected piece of all: the weight of our civilization itself. The groundwater we have pumped out of aquifers, enough water over recent decades to measurably shift the Earth's axis of rotation, has changed not just how long each day is, but literally where the North Pole points. Not by a geologically dramatic amount, by a few centimetres, but it is measurable, it is real, and it happened because of us. This is the story of what is happening to Earth right now, at a level of physical reality that most people never think about. It is a story about the hidden machinery of this planet, the layered, coupled, interacting systems that determine the rhythm of your days without your awareness or consent. It is a story about what happens when that machinery is pushed beyond the range of conditions it has experienced in recent geological history, and it is ultimately a story about what we are doing to a planet whose operating parameters we are only beginning to understand. Let's start at the beginning. Let's start with the day that shouldn't have been as short as it was. Chapter 1. The day that was too short, and what it forced scientists to confront. A day is 24 hours. You have known this since you were a child. It is perhaps the single most reliable fact in your daily experience. The sun rises, the sun sets, the Earth has turned once, and 24 hours have passed. This is the foundation on which all of human timekeeping, scheduling, and navigation has been built for thousands of years. The length of a day is not something that changes. It is not something you have to worry about. It is a given. Except that it is not a given. It never was, and the atomic clocks that have been tracking Earth's rotation with extraordinary precision since the 1970s have been quietly, patiently accumulating evidence that the length of a day is not constant. It fluctuates, it varies, and over the past few decades, it has been getting shorter. Let me explain what we mean by the length of a day, because there are actually two different things that phrase can refer to, and the distinction matters. The first is the solar day, the time it takes for the Earth to rotate from one noon to the next noon, measured relative to the Sun. That is very close to 24 hours on average. The second is the sidereal day, the time it takes for the Earth to complete one full rotation relative to the distant stars. That is approximately 23 hours, 56 minutes, and 4 seconds. The difference between the two arises because the Earth is also orbiting the Sun as it spins, so it has to rotate a tiny bit extra each day to bring the Sun back to the same position in the sky. When scientists talk about the length of a day changing by milliseconds, they are talking about deviations from the standard 24-hour solar day, tiny fluctuations in how fast or slow the Earth is spinning relative to that baseline. These fluctuations are measured by comparing the rotation of the Earth to the ultra-precise ticks of atomic clocks, which keep time based on the quantum mechanical behavior of atoms rather than on any mechanical or astronomical process. Atomic clocks lose or gain less than 1 second over billions of years. They are, for practical purposes, perfect timekeepers. Compared to those perfect timekeepers, the Earth is an irregular timekeeper. Its rotation speeds up and slows down in response to a complicated set of factors: the movement of fluids in the outer core, the redistribution of mass in the atmosphere and oceans, the tidal forces exerted by the moon, the slow rebound of the crust from the last ice age, and various other processes that all contribute their tiny effects to the overall spin rate of the planet. Geophysicists call these variations changes in the length of day, or LOD for short, and they measure them in milliseconds. For most of the period of precise atomic timekeeping, roughly from the 1970s through the 2010s, the overall trend in the length of day was toward longer days. The Earth was slowing down very gradually, primarily because of tidal friction from the Moon. The Moon's gravity raises tidal bulges in Earth's oceans, and as the Earth rotates beneath those bulges, there is a frictional drag that very slowly transfers rotational energy from the Earth to the Moon. This process has been lengthening Earth's days for billions of years. The day was significantly shorter when dinosaurs were alive, and shorter still when the Earth was young. This slow lengthening is well understood, well measured, and entirely expected. But something changed around 2016. The Earth stopped following the expected pattern of gradual slowing. Instead, it started spinning faster. The length of day started getting shorter. Not dramatically, not in a way you could feel, but measurably, consistently, in a direction that was the opposite of what the long-term trend predicted. Between 2016 and 2022, scientists recorded some of the shortest days ever measured. And then, on June 29th, 2022, came the record breaker, a day that was 1.59 milliseconds shorter than the standard 24 hours, a new all-time record for the era of precise timekeeping. This was not, by any reasonable standard, a catastrophe. 1.59 milliseconds is a duration so brief that no human sense organ can detect it. Your entire life will not be meaningfully affected by the fact that that particular day was 1.59 milliseconds shorter than expected. But the record broke in a direction that demanded explanation, because it was part of a pattern, and the pattern suggested that something was changing in the machinery of the planet. What caused it? The honest answer is several things at once, and scientists are still working out the relative contributions of each. But the investigation triggered by this accelerating pattern of shorter days has led researchers into some of the most surprising corners of Earth science, and what they have found there is both fascinating and, in some cases, genuinely concerning. One of the leading suspects in the short day mystery is atmospheric and oceanic variability. The atmosphere of Earth is not a fixed, static shell. It is a fluid system that moves mass around continuously. Storms, pressure systems, seasonal temperature gradients, all of them shifting enormous quantities of air from one place on the planet to another. When mass moves closer to the axis of rotation, the planet spins faster, just as a skater spins faster with arms pulled in. When mass moves away from the axis, the planet slows. Seasonal patterns of atmospheric circulation cause predictable, well-documented fluctuations in the length of day throughout each year. El Niño events in the Pacific Ocean, which involve massive redistributions of warm water, produce detectable changes in the rotation rate. The overall variability of the atmosphere is one of the largest short-term drivers of day-length changes. But atmospheric and oceanic variability alone does not fully explain the observed trend towards shorter days from 2016 onward. Scientists who have modelled the contributions of atmospheric and oceanic effects and subtracted them from the observed rotation changes still find a residual, a shortening of days that cannot be accounted for by the surface fluid layer alone. Something deeper is contributing. That something deeper, many scientists believe, involves the fluid outer core of the Earth, the churning ocean of liquid iron 2,900 kilometers beneath your feet. The outer core is responsible for generating Earth's magnetic field through a process called the geodynamo, and it interacts with the solid mantle above it and the solid inner core below it in ways that are still being actively researched. Changes in the flow patterns of the outer core can exchange angular momentum with the mantle, speeding up or slowing down the planet's rotation by tiny but measurable amounts. There is growing evidence that a phenomenon called a geomagnetic impulse, a rapid change in the strength of the magnetic field that propagates through the core, can trigger detectable changes in the length of day within months to years. What this means is that the record-breaking short day of June 29th, 2022 was not simply a surface phenomenon. It was, at least in part, a signal from the deep interior of the planet, a tremor in the core propagating outward through the mantle, expressing itself at the surface as a tiny change in the rate at which the planet spins. The atmosphere and ocean were responding to each other, and simultaneously, the core was doing something of its own, and the combination of all these interacting perturbations produced a day that was 1.59 milliseconds shorter than it should have been. And then scientists started looking at what the core was doing, and that is where things got genuinely strange. Chapter 2. The Earth is not what you think it is: layers, flows, and hidden machinery. Most of us carry around a mental image of the Earth that was installed somewhere around the 3rd grade and never significantly updated. In that image, the Earth is a layered sphere, thin rocky crust on the outside, thick mantle of rock underneath, liquid outer core of iron below that, and a solid inner core of iron right at the centre. The crust is where we live. The mantle is very hot rock that flows very slowly. The outer core is molten metal that moves. The inner core is a solid ball of iron as hot as the surface of the sun, sitting at the very centre of our world, compressed into solidity by the weight of everything above it. That basic picture is correct in its broad outlines, but it is missing almost everything that makes the Earth's interior scientifically interesting, and scientifically alarming when you start to understand what is changing. Let's start with the scale, because scale matters enormously when thinking about Earth's interior. The Earth has a radius of about 6,371 kilometers from the surface to the centre. The crust, the rocky shell we live on, drill into and mine, is on average about 30 kilometers thick on the continents and about 7 kilometers thick under the oceans. That is the entirety of the world we directly experience, a shell less than 0.5% of the Earth's radius. Everything below the crust is terra incognita in the most literal sense. No human artifact has ever penetrated more than 12 kilometers into the crust, a project that took the Soviet Union decades and still fell short of the mantle by a significant margin. Below the crust is the mantle, extending from the base of the crust down to about 2,900 kilometers depth. The mantle makes up about 84% of Earth's total volume. It is made of silicate rock, the same general family of materials as the crust, but under such enormous pressure and temperature that it behaves over geological timescales like a viscous fluid. The mantle flows. Not quickly. The rates of flow are measured in centimeters per year, but it flows. This slow mantle convection is what drives plate tectonics. The plates of the crust are essentially carried around on the surface of a very slow conveyor belt driven by temperature gradients in the mantle. Hot material rises from depth, spreads laterally, cools, and sinks again, carrying the plates above it and producing the earthquakes and volcanoes and mountain-building events that shape the surface of the planet. Below the mantle is the outer core, extending from about 2,900 kilometers to about 5,100 kilometers depth. This is liquid iron, or more precisely an alloy of iron and nickel with some lighter elements mixed in, kept liquid by the extreme temperature despite the extreme pressure. The outer core is in constant turbulent motion, driven by a combination of thermal convection and the Coriolis effect from Earth's rotation. This flowing, electrically conductive iron generates the Earth's magnetic field through a self-sustaining dynamo process. Without the outer core's churning motion, there would be no magnetic field. Without the magnetic field, the solar wind would strip away our atmosphere the way it has stripped away Mars's atmosphere. The outer core is not just a scientific curiosity. It is, indirectly, a prerequisite for the existence of complex life on the surface. At the very center, below the outer core, is the inner core, a solid sphere of iron and nickel with a radius of about 1,220 kilometers, slightly smaller than the Moon. The temperature at the inner core is estimated at roughly 5,000 to 7,000 Kelvin, comparable to the surface of the Sun. Despite that extraordinary temperature, the pressure at the center of the Earth is so immense, about 3.6 million atmospheres, that the iron remains solid rather than melting. It has been crystallizing out of the surrounding liquid outer core for about 1 billion to 3.5 billion years, growing slowly as the planet cools and the boundary between liquid and solid creeps inward at a rate of perhaps a millimeter per year. Now, the key thing to understand about all of these layers is that they are not isolated. They interact. They exchange mass, energy, and angular momentum across their boundaries in ways that create a coupled, dynamic system whose behavior is far more complex and far less predictable than a simple layered model suggests. The outer core interacts with the mantle above it at what is called the core-mantle boundary. This boundary is one of the most significant interfaces in the Earth's interior, a sharp transition from the silicate rock of the lower mantle to the liquid iron of the outer core, with a temperature contrast of perhaps 1,000 degrees and a density contrast that makes the interface itself physically sharp. But it is not a smooth, static boundary. The outer core fluid flows along the base of the mantle, and the topography of the core mantle boundary, the bumps and valleys in the underside of the mantle, influences how the outer core flows and therefore how the geomagnetic field is generated. Features at the core mantle boundary have been linked to specific features of the magnetic field at the surface, thousands of kilometers above. The inner core interacts with the outer core at a different boundary, the inner core boundary, or ACB. The inner core is not simply sitting passively inside the outer core. There is growing evidence that it rotates, and that its rotation rate is different from that of the overlying mantle and crust. A solid sphere inside a liquid sphere is free to spin at a different rate than the surrounding fluid, subject to the electromagnetic and gravitational coupling between the layers. Estimates of the inner core's differential rotation have varied substantially between different studies, ranging from slightly faster than the mantle to slightly slower, and for a long time the scientific consensus was that the inner core was rotating slightly faster, meaning it was gradually moving ahead of the mantle's rotation, completing each rotation in slightly less time. And then something happened to change that picture. Something that, when it was published in a major scientific journal in early 2023, triggered a significant amount of attention, and not a small amount of alarm, in both the scientific community and the broader public. The inner core appears to have changed, not slightly, not ambiguously. The data suggests it may have reversed the direction of its differential rotation, that it is now moving in the opposite direction relative to the mantle than it was previously. And the timing of this reversal, as best as it can be estimated from the seismic data, is approximately the same period during which the Earth's surface rotation has been producing those anomalously short days. Before we discuss what that reversal might mean, let's talk about how we know anything at all about what the inner core is doing. Because you cannot send a probe to the center of the Earth. You cannot drill there. You cannot observe it directly by any method currently conceivable. What you can do, and what geophysicists have been doing with increasing sophistication for decades, is listen to the echoes of earthquakes. Chapter 3. The inner core is doing something unexpected, and nobody is quite sure what. Every major earthquake produces seismic waves that travel through the Earth's interior in predictable ways. Some of these waves travel along the surface, others plunge deep into the planet, refract at each major boundary between layers, and emerge on the far side. The travel times of these waves, how long it takes for them to travel from the earthquake's location through the Earth to a seismometer on the other side of the planet, depend on the physical properties of every layer they pass through. They depend on density, temperature, composition, and, critically, any internal structure or anisotropy within each layer. The inner core is anisotropic. This means that seismic waves travelling through it in different directions travel at slightly different speeds. Waves travelling roughly parallel to the Earth's rotation axis move faster than waves travelling through the equatorial plane. This anisotropy was discovered in the 1980s and is now well established. Its cause is believed to be the alignment of iron crystals within the inner core, an alignment that is thought to reflect the history of the inner core's growth and rotation. Here is the critical insight for understanding inner core rotation. If the inner core is rotating relative to the mantle, if it is gradually spinning ahead of or behind the rest of the planet, then the angle at which seismic waves travel through the inner core changes over time. Because the anisotropic structure of the inner core is fixed relative to the inner core itself and not relative to the mantle, as the inner core rotates, the effective orientation of its anisotropy shifts when viewed from a fixed surface location. This means that the travel times of seismic waves that pass through the inner core, measured by seismometers at fixed locations on the surface, should change over time, slowly drifting as the inner core's orientation changes. And this is exactly what geophysicists observed starting in the 1990s. By comparing the travel times of seismic waves from similar earthquakes recorded at the same seismometer stations over periods of years and decades, they found that the travel times were indeed changing slightly, consistent with the inner core rotating eastward, in the same direction as the rest of the Earth's surface but slightly faster, at a rate of perhaps a fraction of a degree per year. This was remarkable on its own. A solid sphere at the centre of the planet 5,000 kilometres below the surface, rotating independently of everything above it. It was simultaneously deeply strange and perfectly consistent with the physics of a solid body embedded in a conducting fluid inside a rotating magnetic field. The electromagnetic coupling between the inner core and the outer core, the way the rotating magnetic field generated by the outer core exerts a torque on the electrically conductive inner core, is sufficient to explain differential rotation of the kind observed. The inner core should rotate somewhat independently. The question was always by how much and in which direction. And then the picture started getting complicated. Different research groups using different seismic datasets and different analytical methods started arriving at different answers. Some studies found the inner core rotating faster than the mantle. Others found it slower. Some found evidence for oscillations. The inner core speeding up, then slowing down in a quasi-periodic pattern. The discrepancies were not simply the result of measurement error. They reflected the genuine difficulty of extracting precise information about a body you cannot observe directly from the indirect, sparse and noisy evidence of seismic wave travel times. The 2023 study that attracted the most attention came from Yi Yang and Xiaodong Song at Peking University, published in Nature Geoscience. They analysed a specific category of seismic data, pairs of earthquakes in the same location, separated by decades, whose waves travelled through the inner core to the same seismometer stations. By comparing the travel times of these earthquake pairs at multiple stations around the world, they found that the inner core's rotation, which had been moving ahead of the mantle since at least the early 1970s, appeared to have stalled around 2009 and then reversed direction after that. The inner core, in other words, appeared to have switched from rotating slightly faster than the mantle to rotating slightly slower, with the transition occurring around 2009 and the reversal becoming clearer in the years since. The authors of the study proposed that this reversal is not a one-time anomaly, but part of a long-term oscillation, a back-and-forth pattern in the inner core's differential rotation with a period of roughly 70 years. They connected this proposed oscillation to well-documented 70-year oscillations in the length of day, the long-period variations in Earth's rotation rate that have been observed in precise astronomical data going back to the 19th century, and to corresponding oscillations in the strength and structure of the geomagnetic field. Their suggestion was that all of these phenomena are connected through the mechanics of angular momentum exchange between the inner core, the outer core, the mantle, and the surface. The reaction from the scientific community was mixed, which is exactly what you would expect for a bold claim based on difficult data. Some researchers found the evidence compelling, others pointed to alternative interpretations of the seismic data. Several groups published follow-up analyses arguing that the inner core's behavior was more ambiguous than Yang and Song's paper suggested, that the seismic waves might be telling us about changes in the inner core's structure, rather than changes in its rotation, and that these two possibilities are difficult to distinguish with current data. This is how science works. A striking result gets published. Other scientists dig into the data. Questions get raised. The picture becomes more complicated before it becomes clearer. What we can say with confidence is that something is happening in the inner core, that the seismic data is changing in ways that require explanation, and that whatever is happening is physically connected to the variations in Earth's rotation rate that produced the record-breaking short days we started this chapter with. Let us be specific about that connection, because it is subtle but important. The inner core interacts with the overlying mantle through two types of coupling: gravitational coupling, in which the gravitational attraction between the density irregularities of the inner core and those of the mantle exerts a torque on each layer, and electromagnetic coupling, in which the magnetic field generated by the outer core interacts with both the inner core and the lower mantle. These coupling mechanisms allow angular momentum to be transferred between the inner core, the mantle and crust, and thus over longer timescales, whilst the outer core as well. When the inner core changes its rotation rate, the mantle and crust must respond by changing their rotation rate in the opposite direction to conserve total angular momentum. This means that an inner core that slows its forward rotation relative to the mantle corresponds, via angular momentum conservation, to a slight speeding up of the mantle and crust, a slight shortening of the length of day at the surface. This is the connection. The inner core reversing its differential rotation is, if the Yang and Song interpretation is correct, the deep Earth process contributing to the anomalously short days measured at the surface. The planet's most secret interior and the length of your waking day are linked through the physics of spinning objects and the exchange of angular momentum between layers separated by thousands of kilometers of solid and liquid rock. The inner core is one piece of the puzzle. It is the piece that sits deepest, the piece that is hardest to observe and hardest to model, and arguably the piece whose behavior is most surprising. But it is not the only piece. While the inner core has been doing whatever it has been doing in the depths, the surface of the planet has been experiencing something far more visible, far more measurable, and in some ways far more immediate in its implications. The ice is disappearing, and the physics of what that means for the rotation of the planet is both straightforward and alarming. Chapter 4. 400 billion tons. The weight that isn't there anymore. There is a number that I want you to hold in your mind for a moment before we discuss what it means. 400 billion tons. 400 billion tons. That is the approximate mass of ice that disappears from the Earth's polar regions and mountain glaciers every single year. Not 400 billion tons that melts and refreezes in an annual cycle. That amount is much larger and represents the normal seasonal variability of ice formation and loss that has characterized Earth's climate for millions of years. The 400 billion tons I'm referring to is the net loss, the amount that melts and does not come back, the amount that was solid ice at the beginning of the year and becomes liquid water in the ocean or in river systems by the end of it, the net annual subtraction from the world's cryosphere, the frozen part of the Earth's surface that has been measured, satellite by satellite, glacier by glacier, over the past 2 decades of increasingly precise observation. The primary contributors to this loss are the Greenland ice sheet, the Antarctic ice sheet, and the world's roughly 200,000 mountain glaciers. Each of these systems is losing mass at rates that were not observed, and in many cases not predicted, when climate scientists first began constructing models of ice sheet behavior in the late 20th century. The Greenland ice sheet alone is losing roughly 280 billion tons per year. Antarctica is losing roughly 150 billion tons per year, with losses concentrated in specific vulnerable regions like the West Antarctic ice sheet and the glaciers flowing into the Amundsen Sea. Mountain glaciers globally are retreating at accelerating rates, contributing an additional tens of billions of tons per year. These numbers have enormous implications for sea level rise, for ocean circulation, for regional precipitation patterns, for the availability of fresh water to hundreds of millions of people who depend on glacial melt. Those implications are the subject of extensive research and significant public debate, and they deserve far more attention than they typically receive. But they are not the implications I want to focus on here, because there is a less discussed consequence of all this melting ice that goes directly to the heart of what we have been talking about in this video. When ice melts, it moves. This statement sounds too simple to be important, but it is one of the most consequential physical facts about the current trajectory of Earth's climate. Ice on Greenland is not distributed symmetrically around the planet. Ice on Antarctica is not distributed symmetrically around the planet. The glaciers of the Himalayas are not symmetrically opposite the glaciers of the Andes. The frozen water stored in the cryosphere is distributed across the planet in a specific, non-uniform pattern that has been roughly stable for thousands of years, varying with the seasons and with the millennial scale cycles of ice ages, but maintaining a general pattern that the Earth's rotation has adapted to and reflects in its current parameters. When that pattern changes, when ice in Greenland melts and the water flows into the oceans, mass is redistributed. It moves from the polar regions, where it was stored as ice, to the oceans, where it spreads around the planet. And because the oceans are wider at the equator than at the poles, because water added to the ocean spreads outward toward lower latitudes. Melting ice tends to move mass from high latitudes toward lower latitudes, from regions close to the rotation axis toward regions farther from the rotation axis. Here is where the figure skater physics comes back in. A figure skater pulling their arms inward, moving mass closer to the rotation axis, spins faster. A figure skater extending their arms outward, moving mass away from the rotation axis, and spins slower. The technical term for this phenomenon is conservation of angular momentum. As the distribution of mass in a rotating system changes, the rotation rate changes to keep the total angular momentum constant. The same principle applies to the Earth. When melting ice redistributes mass from the poles toward the equator, Earth's moment of inertia, a quantity that measures how the planet's mass is distributed relative to its rotation axis, increases. When the moment of inertia increases, the rotation rate decreases in order to conserve angular momentum. This means that, all else being equal, the melting of ice sheets and glaciers should be making Earth's days slightly longer, not shorter. And this is indeed one of the documented effects of modern ice melt, a slow, secular lengthening of the day caused by the redistribution of meltwater into the global ocean. It is a small effect on human timescales. The changes involved are fractions of a millisecond per century, but it is real, it is measured, and it points in the direction of longer days over the coming centuries as warming continues and ice continues to disappear. But the story does not stop there, because ice loss does not just change the rotation rate, it changes the axis of rotation itself, the direction in which the rotation pole points, and the evidence that this is happening and that human activity is driving it is one of the most extraordinary and underreported scientific findings of recent decades. The Earth's rotational pole, the point on the surface around which the planet spins, which is very close to but not identical to the geographic North Pole, is not fixed in space. It wanders. It traces a slow, irregular path over the surface of the planet, driven by mass redistributions in the interior and on the surface. This wandering, called polar motion, has been measured with increasing precision for over a century. Before the satellite era, it was tracked using astronomical observations of the apparent position of the pole star. Since the 1990s, it has been measured with extraordinary precision using GPS and other space geodetic techniques. In the mid-20th century, the pole was drifting in a direction roughly toward Canada, south of Greenland toward Hudson Bay. It had been drifting in that general direction for decades, and then, around the year 2000, the direction of polar drift began to change. The pole started drifting in a new direction, away from Canada and toward the coast of Greenland, which sits roughly in the direction of the British Isles if you look from the North Pole. What caused this change? A 2021 study published in Geophysical Research Letters by Shanshan Deng and colleagues, building on earlier work by Surendra Adhikari and Eric Evans at NASA's Jet Propulsion Laboratory, determined that the change in the direction of polar drift was directly attributable to two factors: the melting of ice sheets and glaciers and the depletion of groundwater from terrestrial aquifers. Together, these two processes, both driven primarily by human activity, have redistributed enough mass around the Earth's surface to measurably change which direction the planet wobbles. Let that sink in for a moment. We have moved so much water, by melting glaciers through climate change and by pumping groundwater out of the ground for agriculture and industry, that we have changed the direction in which Earth wobbles. We have shifted the pole of rotation, not by a geologically dramatic amount. The shift since 1990 is on the order of a few meters, But the shift is real, it is measured, and it is ongoing, and it is accelerating. The groundwater component of this story is the one that I find most striking, and I want to spend time on it because it is less well known than the ice melt story and arguably just as important. Between 1993 and 2010, humanity pumped approximately 2,150 gigatons of groundwater out of aquifers, massive underground reservoirs of water stored in porous rock layers, filled over thousands of years by percolating rainwater and snowmelt. This water was pumped out to irrigate crops, to supply cities, to sustain the industrial agriculture that feeds the world's expanding population. It was pumped out in India, in the United States, in China, in the Middle East, in virtually every region where agricultural demand exceeds the natural replenishment rate of surface water. And when it was pumped out of the ground, it did not stay in the ground. It flowed into rivers, evaporated into the atmosphere, was consumed by crops, and eventually ended up mostly in the ocean, redistributed from the continental interiors where the aquifers are concentrated toward the global ocean that rings the planet. The Adhikari and Evans study estimated that this groundwater depletion alone, the removal of 2,150 gigatons of water from the land and its redistribution to the ocean, shifted the Earth's rotational pole by approximately 78 centimeters, or about 80 centimeters toward the east. That is not a rounding error in polar motion data. That is a detectable, significant human-caused shift in the axis around which this planet rotates. We have changed the direction the Earth points. I want to be careful about how I characterize the significance of this. Polar motion of the magnitude we're talking about, centimeters to meters, does not produce dramatic surface consequences. It does not cause geologic catastrophe. It does not meaningfully affect the climate or the seasons or anything that you would notice in your daily life. The Earth is a large and resilient system, and centimeter-scale wobbles in the pole position are routine occurrences that the planet absorbs without drama. But the significance is not in the consequences of this particular wobble. It is in what it tells us about the scale of human intervention in the physical systems of this planet. The Earth's rotational axis is not a fragile thing. It is not easily moved. It takes either an enormous natural process, a major earthquake, a significant change in ice distribution over millennia, a major volcanic eruption, or an enormous human intervention to shift it measurably. And we have shifted it measurably, without intending to, without most people even knowing it was possible, through the cumulative effect of billions of individual decisions to pump water from the ground and burn fossil fuels. We have physically moved the pole of the planet. That is the level at which human civilization is now interacting with the Earth's geophysical systems. Not the crust, not the surface, not the atmosphere and the biosphere in isolation. The rotation of the planet itself, the fundamental physical parameters of this world, how fast it spins, which direction it points, are now measurably within the range of things that human activity modifies. And we are, if anything, accelerating. The rate of ice melt is increasing. The rate of groundwater depletion is increasing in many regions. The atmospheric forcing that drives both of these is increasing. The coupling between all of these surface changes and the deep interior processes, the outer core dynamics, the inner core rotation, the mantle flow patterns, is not zero, though it is indirect and operates on longer timescales. The surface changes are feeding back into the deep machinery of the planet in ways we are only beginning to understand. Every layer is connected to every other layer. Every perturbation propagates. Every gram of ice that melts. Every litre of groundwater pumped from the ground. Every molecule of carbon dioxide added to the atmosphere that traps a little more heat, that melts a little more ice. All of it feeds into a coupled system whose responses are not always linear, not always predictable, and not always slow. The Earth is not a stable platform. It is a dynamic machine. It is a machine that human civilization is now operating without a manual, without an off switch, and mostly without realizing it. We're going to keep pulling on these threads in part 2. The story gets more complicated and more concerning before it gets clearer. End of part 1. Part 2 continues with the magnetic field crisis, the compounding feedback loops, and what all of it means for the world we are inheriting. Chapter 4 continued. The compounding problem. When systems stop behaving independently. Here is what makes the ice loss story more than just an environmental concern. It is also a story about coupling, about the way in which changes at the surface of the planet propagate into deeper systems and trigger responses that are not always intuitive and not always linear. Consider the relationship between ice loss and sea level. When ice melts from Greenland or Antarctica, it adds water to the ocean. This raises sea level globally, on average, across the whole ocean surface. But here is something that is not widely known and is genuinely counterintuitive. Sea level does not rise uniformly everywhere when ice melts. It actually falls near the ice sheets that are losing mass and rises more than the global average far away from them. The reason is gravity. The Greenland ice sheet is an enormous mass of ice, several million cubic kilometers of frozen water. Like any massive object, it exerts a gravitational pull on the surrounding ocean, drawing water toward it. This gravitational attraction raises the sea level near Greenland above what it would be without the ice sheet's presence. When the ice melts and the ice sheet loses mass, its gravitational pull weakens, and the water it had been attracting is no longer held close. The ocean surface near Greenland actually falls slightly, even as Greenland is adding meltwater to the ocean overall, because the loss of gravitational attraction is locally more significant than the addition of meltwater. Meanwhile, the redistributed water flows toward lower latitudes, toward the equator, raising sea levels there by more than the global average. This means that the communities most directly affected by Greenland melt, in terms of sea level, are not in Greenland. They are in places like Southeast Asia, the Pacific Islands, and the coastlines of tropical regions. The physics of melting ice sheets actively redirects their consequences toward the places furthest from the melting itself, and it gets more complicated still. The loss of ice mass from Greenland and Antarctica is causing the land beneath those ice sheets to rebound. The crust is elastic over geological timescales. It deforms under the weight of ice, and when the ice is removed, it slowly rebounds upward, a process called glacial isostatic adjustment. The rebound in Greenland is already measurable. Some parts of the island are rising at rates of several millimeters per year. This vertical movement of the land affects local sea level, affects the drainage of meltwater, and feeds back into the ice dynamics of the remaining ice sheet in ways that complicate projections of future melt rates. This is what geophysicists mean when they say the Earth's systems are coupled. It is not a vague statement about everything being connected. It is a precise technical observation. The ice influences the ocean influences the crust influences the ice, and all of them influence the rotation of the planet, and the rotation of the planet influences the dynamics of the core, and the core dynamics affect the magnetic field, and the magnetic field affects the charged particle environment in the atmosphere, and the charged particle environment may influence cloud formation and precipitation, which influence where ice accumulates and where it melts. These are not loose poetic connections, they are physical links, each one operating through specific, quantifiable mechanisms. The reason the temporal coincidence of all these changes matters, the record short days, the possible inner core reversal, the accelerating ice loss, the shifting poles, is precisely because these systems are coupled. The Earth is not experiencing these changes independently and in isolation. It is experiencing them simultaneously and interactively. The outer core response to changes in mantle conditions is not independent of the surface mass redistribution. The inner core dynamics are influenced by the electromagnetic coupling with an outer core whose flow patterns are themselves responding to changes at the core mantle boundary. The surface changes, the melting ice, the pumped groundwater, the redistribution of mass, are perturbing a system that was in a complex and sensitive dynamical equilibrium, and the propagation of those perturbations through the coupled system is what we are observing in the form of shorter days, shifting poles, and changing seismic signatures. The Earth is telling us something. It is telling us in the language of millisecond deviations in its rotation, in the drift of its magnetic pole, in the travel times of seismic waves through its iron core. Most of those messages are too precise and too technical for anyone to hear without instruments. But they are there, and they are consistent. They are all describing a planet that is in motion, a planet whose deep machinery is engaged with the changes being imposed on its surface, a planet that is responding to us in ways that extend far deeper than we typically imagine our reach to extend. In part 2, we are going to go further into what those responses mean, for the magnetic field, for the long-term stability of the systems we depend on, and for the question of what kind of planet we are leaving behind. The story does not get simpler, it does not get more comforting. but it does get more important the more of it you understand. Chapter 5. The magnetic field is weakening, and it has done this before. There is a shield around this planet. You cannot see it. You cannot feel it. You have never had a single direct sensory experience of it in your entire life, and yet without it, you almost certainly would not be alive. Neither would anything else you have ever seen or touched or eaten or loved. The shield is the Earth's magnetic field, the vast invisible envelope of magnetism generated by the churning liquid iron of the outer core that extends outward from the planet's surface into space, deflecting the constant stream of charged particles flowing outward from the sun. The solar wind is not gentle. It is a continuous high-energy outflow of protons and electrons that, if allowed to interact directly with the upper atmosphere, would gradually strip it away, eroding the ozone layer, ionizing atmospheric molecules, and over geological timescales removing the atmospheric gases that regulate the planet's temperature and protect its surface from ultraviolet radiation. We know this is not hypothetical, because we can see it happening on Mars, which lost its magnetic field roughly 4 billion years ago, and has since had its atmosphere reduced to a thin, cold wisp. Earth's magnetic field has protected us from this fate for the entirety of the time complex life has existed on this planet. It has deflected solar storms, channeled charged particles harmlessly toward the poles where they create the auroras, and maintained the atmospheric conditions that made biological evolution possible. It is, in the most literal sense, one of the primary reasons we are here. And right now, it is weakening. The weakening is not subtle, and it is not new. It has been measured continuously since the first systematic magnetic surveys were conducted in the early 19th century, and it is one of the better documented trends in Earth science. The strength of the global magnetic field, measured in terms of the intensity of the magnetic flux at the surface, has decreased by approximately 9% over the past 170 years. 9% in less than 2 centuries, in a field that has been roughly stable for thousands of years before that. The rate of decrease is faster than anything in the geological record of the past few thousand years, and it has been accelerating in recent decades. The centre of this weakening is a region called the South Atlantic Anomaly, an area stretching roughly from South America across to Africa, where the magnetic field is dramatically weaker than it is elsewhere at the same latitude. The South Atlantic Anomaly is not new. It has been present and growing for centuries, but it has expanded and intensified in recent decades to the point where it creates real operational challenges for satellites passing through it. In the South Atlantic Anomaly, the Van Allen radiation belts, the zones of trapped charged particles that surround the Earth, dip closer to the surface than anywhere else. Satellites passing through this region experience elevated radiation exposure, more frequent electronic glitches, and higher rates of component failure. The International Space Station has documented these effects. GPS satellites experienced them. Several early satellites malfunctioned in ways that were eventually attributed to the anomaly. The South Atlantic Anomaly appears to be getting larger. Recent analyses of satellite data from the ESA's SWARM mission, a constellation of 3 satellites specifically designed to map the magnetic field with high precision, have found evidence that the anomaly may be splitting into 2 distinct lobes, a development that some researchers interpret as a sign of significant changes in the underlying core dynamics that generate the field. The deeper context for the magnetic field's current behaviour comes from the geological record, and this is where things get genuinely interesting. The Earth's magnetic field reverses. It has done so many times in the geological past, switching the positions of magnetic north and magnetic south, with north becoming south and south becoming north over a period of thousands of years. These reversals are recorded in the magnetic signatures of volcanic rocks. As lava cools and solidifies, iron-bearing minerals in the rock align with the ambient magnetic field and freeze in that alignment, creating a permanent record of the field's direction and strength at the time of solidification. Ocean floor spreading creates continuous strips of rock recording the history of the field's polarity, and from these records we know that reversals have occurred hundreds of times in the past 80 million years, at irregular intervals averaging perhaps 200,000 to 300,000 years. The last reversal, called the Matuyama-Brunhes reversal, occurred approximately 780,000 years ago. By the average interval between reversals, we are overdue. We have been overdue for a very long time. The statistical regularity of reversals does not guarantee that one will happen on any particular schedule, and overdue in geology is a relative and imprecise concept. But the combination of long time since the last reversal and the observed weakening of the field has led a number of geophysicists to ask whether we might be in the early stages of an excursion or a full reversal. An excursion is a temporary departure of the field from its current polarity. A partial reversal that does not complete, where the field weakens, becomes disorganized and multipolar, and then recovers and restabilizes in the same polarity it started in. Excursions have occurred multiple times in the past and are recorded in the paleomagnetic record. They are associated with periods of field weakness that, while not as prolonged as full reversals, share some of the same characteristics: weakening overall intensity, the development of multiple magnetic poles, and a more complex and variable field structure. The geological record of field reversals and excursions shows a consistent pattern during the transition period. The field weakens significantly, to perhaps 10 to 20% of its stable polarity strength, before recovering or completing the reversal. During this weak field period, the protection against the solar wind is substantially reduced. High-energy particles that would normally be deflected penetrate deeper into the atmosphere. The radiation environment at the surface increases. The chemistry of the upper atmosphere changes as cosmic rays and solar particles interact with atmospheric molecules in new ways. Whether the current weakening is the precursor to a reversal, an excursion, or simply a temporary fluctuation within the normal range of the geodynamo's variability is something that current science cannot definitively answer. The geodynamo is inherently chaotic. Its behavior is driven by turbulent fluid dynamics in the outer core that are sensitive to initial conditions and not perfectly predictable over long time scales. What we can say is that the field is weaker than it has been at any point in the past few thousand years, that the rate of weakening is faster than anything in the well-dated paleomagnetic record, and that the structural changes in the field, including the expanding South Atlantic anomaly and the possible bifurcation of its two lobes, are consistent with the patterns seen in the paleomagnetic record during periods preceding major field changes, and here is where the connection back to the inner core matters again. The geodynamo, the process generating the magnetic field, is driven by the flow of liquid iron in the outer core. That flow is influenced by the boundary conditions at both the top and bottom of the outer core, the core mantle boundary above and the inner core boundary below. The rotation of the inner core and any changes in that rotation affects the electromagnetic and thermal conditions at the inner core boundary, which influences the convective patterns in the outer core, which influences the structure and strength of the magnetic field generated by those convective patterns. The inner core dynamics we discussed in part 1 are not separate from the magnetic field changes we are discussing now. They are part of the same integrated system, operating at different depths and on different timescales, but physically coupled through the shared fluid medium of the outer core. When geophysicists look at the full picture, the inner core rotation changes, the magnetic field weakening and structural evolution, the acceleration of geomagnetic impulses, the changes in the length of day. They see what looks like an unusually active period in the dynamics of Earth's deep interior, a period in which multiple aspects of the system are changing simultaneously, faster than background rates, in ways that are consistent with a system that is transitioning from one dynamical state to another. Whether that transition is significant or routine, whether it represents the early stages of something major or a fluctuation that will stabilize and resolve, is one of the most actively researched questions in Earth science right now. Chapter 6. Everything talks to everything. The cascade of feedbacks we did not expect. There is a specific kind of nightmare in complex system science. It is called a feedback cascade. It is what happens when a change in one part of a coupled system triggers changes in other parts of the system, which then feed back into the original part, amplifying the initial change, triggering further responses in still other parts of the system, until what began as a small and bounded perturbation becomes a self-reinforcing process that the system cannot easily dampen or reverse. The Earth's climate system has several well-documented potential feedback cascades. The ice albedo feedback is the most famous. As ice melts, the dark ocean surface beneath it absorbs more solar radiation than the reflective ice did, warming the ocean, melting more ice, exposing more dark ocean, absorbing more radiation in an accelerating cycle. The permafrost carbon feedback is another. As permafrost in Arctic regions thaws, The organic material frozen within it decomposes and releases carbon dioxide and methane, greenhouse gases that warm the atmosphere, which thaws more permafrost, which releases more greenhouse gases in another self-reinforcing cycle. The water vapour feedback is the most powerful of all. As warming increases evaporation, more water vapour enters the atmosphere, and water vapour is itself a greenhouse gas, amplifying the warming that drove the increased evaporation. These climate feedbacks are well understood and are already incorporated into the models that generate projections of future climate change. But there is a class of feedbacks that is less well understood and less often discussed, the feedbacks between the climate system and the geophysical systems of the deep Earth. The coupling between what is happening at the surface and what is happening in the crust, mantle, and core. Let us work through some of the most important of these cross-system feedbacks, because they represent the frontier of current understanding and some of the most consequential uncertainties in Earth science. The first is the feedback between ice loss and volcanic activity. This is not hypothetical. It is grounded in solid physical reasoning and supported by historical evidence. The ice sheets that covered large parts of the northern hemisphere during the last ice age were enormously massive, in some regions kilometers thick. The weight of that ice depressed the crust beneath it, pushing it downward and compressing the mantle rock below. When the ice sheets melted at the end of the last glacial maximum, approximately 12,000 years ago, the removal of that weight allowed the crust to rebound. It rose upward, a process still ongoing today in Scandinavia and Canada. But the removal of the weight also reduced the pressure on the mantle rock beneath the glaciated regions, and reduced pressure on mantle rock decreases its melting point. This process, decompression melting, caused an increase in volcanic activity in deglaciated regions. Iceland, which sits atop a mid-ocean ridge and was heavily glaciated during the last ice age, showed a dramatic increase in volcanic eruption frequency immediately after deglaciation, roughly 30 times more volcanic activity in the centuries immediately following major ice loss than in the preceding glacial period. The implication for the present is uncomfortable. As Greenland and Antarctica lose ice mass, and as the ice continues to thin and retreat, the crust beneath is being unloaded. The process of glacial isostatic adjustment is already underway in Greenland, where some regions are rising by several millimeters per year. As the pressure on the underlying mantle decreases, the conditions for decompression melting are created. This is not a fast process. The timescale for mantle response to surface unloading is thousands to tens of thousands of years, but it is a real physical effect, and on the timescales of civilizational concern, it means that the ongoing melting of ice sheets is gradually modifying the pressure conditions in the underlying mantle in ways that could influence volcanic and seismic activity over coming centuries and millennia. The second feedback is between sea level rise and seismic activity. The ocean floor is not flat and it is not static. It flexes under the weight of the water above it, and when that weight increases, as it does during sea level rise, the flexure changes. Where ocean water accumulates near coastlines and seafloor rises, the increased load compresses the underlying crust and changes the stress state on faults in the region. There is geological evidence from the end of the last glacial maximum that the rapid sea level rise of that period, sea levels rose by roughly 120 meters over a period of several thousand years, was associated with changes in the distribution of seismic activity around the world. Fault systems that were previously in a certain stress state were pushed into different stress states by the redistribution of water mass, changing the timing and location of earthquakes. The current sea level rise, driven by thermal expansion of the oceans and by melting ice, is slower than the post-glacial rise by a considerable margin, but it is ongoing and accelerating, and its effects on crustal stress accumulate over time. Researchers studying the interaction between sea level rise and seismicity have found statistical correlations between seasonal ocean loading variations and the timing of earthquakes in coastal and submarine fault systems, suggesting that even relatively small changes in water mass distribution can influence the stress state of nearby faults. What this means over the coming centuries, as sea levels continue to rise, is an open research question, but it is a question that belongs in the conversation about the full range of consequences of climate change. The third feedback is between atmospheric changes and the length of day. We established in part 1 that the atmosphere is one of the largest contributors to short-term variability in Earth's rotation rate, as seasonal and interannual shifts in atmospheric mass distribution alter the planet's moment of inertia. What happens to this effect as the climate changes? The answer is that a warmer atmosphere is a different atmosphere, different in its mass distribution, its pressure patterns, its seasonal cycles, its circulation regimes. Models of future climate states predict significant changes in atmospheric circulation patterns, in the location and intensity of the jet streams, in the distribution of high and low pressure systems. All of these changes will have corresponding effects on the distribution of atmospheric mass and therefore on the length of day. Quantifying this effect is difficult because it requires accurate climate models run forward in time, and climate models have genuine uncertainties at regional scales. But the qualitative direction is clear. Climate change will alter the distribution of atmospheric mass in ways that change the Earth's rotation rate, on top of and interacting with the direct effect of ice melt redistributing ocean mass. The length of day in a warmer world will be different from the length of day today, not dramatically, not in ways you would notice, but measurably in ways that will require ongoing adjustments to the timekeeping systems that global infrastructure depends on. The most important feedback cascade of all, however, is the one that is happening entirely within the human domain, and it is the one that most directly connects what we are discussing to decisions that are being made right now, by governments and corporations and individuals about energy systems and land use and water management. The feedback works like this. We burn fossil fuels, which warms the climate, which melts ice, which raises sea levels, which threatens coastal infrastructure and agricultural systems, which creates resource scarcity and population displacement, which generates political instability, which makes coordinated global action on climate change harder to sustain, which allows fossil fuel use to continue or increase, which warms the climate further. This is not a speculative feedback loop. Its components are already documented and operating. The question is whether the positive reinforcements in this loop will be counteracted by other factors, by technological change, by policy intervention, by the economic forces that are progressively making clean energy cheaper than fossil energy, or whether the positive feedbacks will dominate. The geophysical feedbacks we have been discussing are slower and less immediately consequential than the socio-political feedbacks, but they are real and they compound over longer timescales. A planet that is losing ice is a planet that is redistributing mass, changing its rotation, potentially increasing volcanic and seismic activity in ice-covered regions, altering the stress states of offshore fault systems, and modifying the atmospheric circulation patterns that govern regional climate. Each of these changes feeds back into the others in ways that are difficult to fully model and have not been fully incorporated into the integrated assessments that inform policy decisions. What the science is telling us, in aggregate, is that we are operating a complex, coupled, non-linear system, and we are pushing it in a direction it has not been pushed in the recent geological past, at a rate it has not experienced in any period we can confidently compare to, using models that capture the most important first-order effects but likely miss some of the second- and third-order coupling effects that become increasingly important as the perturbations grow larger. Chapter 7. The human fingerprint runs deeper than we thought. Let us step back from the details for a moment and look at the full picture. Because what we have been building toward, chapter by chapter, is a specific and rather extraordinary conclusion about the nature and scale of human influence on this planet. The standard way to think about human impact on Earth is in terms of the surface: deforestation, ocean acidification, habitat loss, atmospheric composition changes, species extinction. These are the impacts that are visible, measurable, and most directly consequential for the living systems of the planet. They are real, they are serious, and they deserve every bit of the attention they receive. But the story we have been telling in this video is about a different dimension of human impact, an impact that runs not across the surface but downward, through the layers of the planet, reaching into systems that operate on geological timescales, and that most people would intuitively assume to be entirely beyond the reach of anything we could do. And the evidence we have reviewed suggests that this assumption is wrong. Let us catalogue what human activity has been shown, with solid scientific evidence, to have measurably changed in the geophysical systems of the planet. We have changed the Earth's rotation rate. Ice melt driven by anthropogenic greenhouse gas emissions is redistributing mass from the polar regions to the global ocean, altering Earth's moment of inertia and producing a measurable secular trend toward longer days. This effect is small on short timescales but cumulative and ongoing. It is in the opposite direction from the shorter days produced by atmospheric and core dynamics, and the balance between these effects determines the net change in day length that atomic clocks register. The anthropogenic component of this change is real and has been quantified in peer-reviewed research. We have changed the direction of Earth's rotational axis. The combination of ice sheet mass loss and groundwater, depletion, both driven primarily by human activity, the former by climate change and the latter by agricultural and industrial water use, has redistributed enough mass to shift the Earth's rotational pole by tens of centimeters in a new direction since the 1990s. This was demonstrated in a study published in Geophysical Research Letters in 2021, which was able to quantify the separate contributions of ice loss and groundwater depletion to the observed polar drift and found that human activity was the dominant driver of the change in drift direction that began around 2000. We have changed the rate of crustal rebound, the isostatic rebound of the crust in ice-covered regions, the slow upward movement of the land as the weight of ice is removed, is a geological process that normally operates over thousands to tens of thousands of years in response to ice age cycles. The current rate of rebound in Greenland and parts of Antarctica has been accelerating because ice is being removed faster than it was during any comparable period in the recent geological record. In some regions of Greenland, the rate of crustal uplift is faster now than it has been at any point since the end of the last ice age. Human-driven ice loss is accelerating a geological process. We have changed the stress state of ocean floor faults and potentially changed the timing and distribution of seismic and volcanic activity in ways that will become more significant as sea level rise continues to accumulate. The evidence for this effect is indirect and the quantification is uncertain, but the physical mechanism is sound and the historical analogy with post-glacial deglaciation is well documented. We have changed the pressure conditions in the upper mantle beneath previously glaciated regions, creating conditions for enhanced decompression melting in the long run. This effect will operate on timescales of centuries to millennia rather than decades, but it is a physical consequence of the ice mass loss we are currently driving. None of these effects, individually, is catastrophic on short timescales. The shift in Earth's axis does not cause earthquakes or tsunamis. The change in day length does not affect agriculture or navigation in any meaningful way. The acceleration of crustal rebound does not immediately endanger coastal populations. The geophysical changes we are producing are real but subtle. They are measured in millimeters and milliseconds and fractions of a degree, not in the dramatic units of immediate human experience, but they are important for two reasons that go beyond their immediate magnitude. The first is what they tell us about the scale of human influence. The geophysical systems we have been discussing, Earth's rotation, its axis orientation, its crustal dynamics, its mantle pressure distribution, are not small or fragile systems. They are among the most massive and most energetically powerful systems on the planet, operating at scales that dwarf anything human civilization has ever built. The fact that we can measure our fingerprint on these systems, the fact that human activity is now one of the drivers of changes in phenomena as fundamental as the length of a day or the direction a planet points, is a statement about the magnitude of our impact that should be read with considerable gravity. We have entered a geological epoch, the Anthropocene, in which human activity has become a primary driver of Earth system change at multiple scales simultaneously. This is not a political statement. It is a geophysical one, supported by measurements of rotation rates, pole positions, crustal rebound rates, atmospheric composition, ocean temperature and acidity, ice mass, and species extinction rates. The convergent evidence from all of these independent measurement systems points to the same conclusion. Human activity is now operating at a scale that registers in the deep Earth, not just the surface Earth. The second reason these geophysical changes are important is that they are, in most cases, irreversible on any timescale relevant to civilization. The ice that has already melted will not refreeze on a timescale of centuries, even if greenhouse gas emissions were stopped tomorrow. The aquifers that have been depleted will not refill on a timescale of centuries, even if pumping stopped tomorrow. The crustal rebound already set in motion by current ice loss will continue for thousands of years after the ice loss itself stops. The changes we are making to the geophysical parameters of this planet are not reversible through any action we are currently capable of taking. They can be stopped from getting worse, they cannot be undone, This is the full weight of the human fingerprint on Earth's deep systems. Not just a changed atmosphere and a warmer ocean, a changed planet physically, geophysically, measurably different in its rotational dynamics and axial orientation from the planet that existed before industrial civilization. A planet that will carry the physical record of what we have done to it for millions of years, in the signatures of its rocks, in the dynamics of its core, in the rebound of its crust and the redistribution of its mass, long after civilization itself has either solved its current problems or become one of geology's cautionary tales. Chapter 8. What comes next? The planet we are actively building. There is a concept in Earth science called a tipping point. It is the threshold at which a system that has been changing gradually and continuously, under external forcing, crosses into a qualitatively different regime, one where the changes become self-sustaining, where the system's own internal dynamics drive further change even if the external forcing is removed or reduced. Tipping points are dangerous precisely because they are often not clearly marked. The system approaches them gradually, behaving normally right up to the threshold, and then the dynamics shift and what was a manageable bounded process becomes something much harder to contain. The Earth's climate system has several candidate tipping points that have been the subject of intense research. The West Antarctic ice sheet, a marine-based ice sheet whose base sits below sea level, is considered potentially vulnerable to a runaway instability called marine ice sheet instability, in which the grounding line retreats progressively into deeper water, causing the ice to flow faster and thin more rapidly in a self-reinforcing process. If this instability is triggered, the eventual collapse of the West Antarctic ice sheet is thought to be possible even without further warming. The dynamics of the ice sheet itself, once destabilized, would drive the process to completion. The potential sea level contribution from West Antarctic ice sheet collapse is roughly 3 to 4 meters. The Greenland ice sheet has its own potential tipping points. At some threshold of warming, surface melt rates may exceed the rate at which snowfall can replenish the ice sheet, committing the sheet to an irreversible long-term decline even if temperatures are subsequently stabilized. The ice sheet's elevation also plays a role. As the ice surface lowers due to melt, it sits at a lower altitude where temperatures are higher, increasing melt rates in a feedback that could accelerate the ice loss over centuries. Full melting of the Greenland ice sheet would contribute approximately 7 meters of sea level rise. The permafrost tipping point is perhaps the most consequential for near-term climate forcing. There are estimated to be approximately 1.5 trillion tons of organic carbon stored in Arctic and subarctic permafrost, roughly twice the amount currently in the atmosphere. As permafrost thaws, this organic material decomposes and releases carbon dioxide and methane into the atmosphere. If a sufficient fraction of this carbon is released rapidly enough, it could overwhelm human mitigation efforts and push atmospheric greenhouse gas concentrations to levels that cause additional warming, additional thaw, and additional carbon release, a runaway permafrost feedback. Current climate models are uncertain about the magnitude and timing of these feedbacks, in part because the processes involved operate at spatial scales below the resolution of global models, and in part because the permafrost ecosystems contain biological complexity that is difficult to capture in physical models. What the observations tell us is that permafrost thaw is already occurring faster than the most pessimistic projections of 15 years ago that thermokarst lakes, bodies of water formed by the collapse of thawing permafrost, are expanding rapidly across the Siberian and Alaskan landscape, and that methane emissions from Arctic regions are increasing. Now let us connect these climate tipping points back to the geophysical themes of this video, because the connection is direct and important. Each of the climate tipping points we have discussed involves a large-scale redistribution of mass on the surface of the planet. The West Antarctic ice sheet holds roughly 2.2 million cubic kilometers of ice. If that ice were to collapse and melt into the ocean over centuries, the resulting mass redistribution would be enormous, comparable to or larger than the ice loss that has already shifted Earth's rotational pole measurably since 1990. The Greenland ice sheet holds roughly 2.85 million cubic kilometers. The permafrost holds vastly more mass than either, though its melting contributes primarily through gas release rather than direct water redistribution. What this means is that if one or more of these tipping points is crossed, the geophysical consequences we have been discussing throughout this video, the changes to Earth's rotation rate, to the direction of the rotational axis, to the crustal stress distribution, to the pressure conditions in the upper mantle, will not simply continue at their current rate. They will accelerate as the mass redistribution associated with ice sheet collapse vastly exceeds anything that has occurred so far. The Earth's geophysical systems will need to respond to a significantly larger perturbation than they have experienced in the recent past, and the responses of those systems, some of which operate on timescales of thousands of years and are only beginning to register the changes of the past century, will continue to unfold long after the triggering events have passed. The planet we are building, the planet that the accumulated choices of the current and coming decades will construct, is one that has departed significantly from the geophysical baseline of the Holocene. It is a planet with a different rotation rate, a different axial orientation, a modified crustal stress state, altered upper mantle pressure conditions, a weakened magnetic field in an uncertain transitional state, and an ice distribution that may be on a trajectory toward configurations not seen since the Pliocene, 3 million years ago. We do not fully know what kind of planet this will be. The uncertainties are genuine and significant. The Earth is a complex, coupled, non-linear system, and our models of it are powerful but incomplete. There are processes we have not fully characterized. There are feedbacks we have not fully quantified. There are tipping points whose thresholds we cannot precisely locate until we have crossed them. But we know enough to say something clear. The Earth's geophysical systems, the systems that determine the length of your days, the direction the planet points, the strength of the field that shields you from solar radiation, the stability of the ice that stores the water that sustains your civilization, are not passive, static backdrops to human history. They are active, coupled, dynamic systems that respond to perturbations and that have their own internal dynamics, their own timescales, their own thresholds. They have absorbed the perturbations of the industrial era and are responding to them, slowly and at depth, in ways we are only beginning to detect and understand with our atomic clocks and our satellite gravimeters and our seismic networks. The response is already underway. The days are getting shorter, even as the longer-term trend from ice melt pushes them toward being slightly longer. The pole has moved. The inner core may have reversed its differential rotation. The magnetic field is weakening and reorganizing. The crust is rebounding. The mantle is beginning to respond to the change in the weight it has been carrying. All of these changes are small on human timescales. All of them are significant on geological ones, and all of them are accelerating. Conclusion. Let us come back to June 29th, 2022, the shortest day ever recorded. 1.59 milliseconds faster than a standard 24-hour rotation. A number so small that no human being felt it, noticed it, or was meaningfully affected by it in any direct way. A record that was registered only by atomic clocks, and then analysed by scientists who were already looking at a planet that had been producing anomalously short days for several years. We started there, and we used that thread to unravel something much larger. Something that turned out to be not one story but many stories, all of them intertwined, all of them describing different aspects of a single, underlying reality. That the Earth is a layered, coupled, dynamic system whose deepest components are in motion, and whose surface perturbations propagate inward, and whose internal changes propagate outward, and that all of these motions, from the rotation of the iron inner core to the redistribution of surface water, are happening simultaneously and are connected to each other through physical laws that do not care whether we understand them or not. The inner core is doing something that is contested and debated in the scientific community and not yet fully resolved, but something nonetheless. It is not doing nothing. And whatever it is doing is connected to variations in the length of your day through angular momentum exchange between layers separated by thousands of kilometers of solid and liquid rock. The ice is disappearing at 400 billion tons per year, and that disappearance is physically moving the pole of the planet, physically changing the length of each day, physically unloading the crust and setting in motion a glacial rebound that will continue for thousands of years. The groundwater we have pumped from the Earth has added to this effect with measurable consequence. We have changed where the planet points and how fast it spins, and we did it without most people knowing it was possible, through the accumulated weight of billions of individual decisions made for reasons that had nothing to do with planetary geophysics. The magnetic field is weakening. Not catastrophically, not immediately, but measurably and significantly. in ways that connect to the dynamics of the deep core that also connects to the rotation anomalies we started with. Whether the weakening is the precursor to a reversal, an excursion, or a temporary fluctuation is uncertain. What is certain is that the field is weaker than at any point in the past few thousand years, and that the structural changes observed in it are consistent with significant reorganization of the geodynamo's behavior. The feedback loops are active. The coupling between climate and geology runs deeper than the surface. Ice loss influences volcanic risk in deglaciated regions. Sea level rise modifies crustal stress. Atmospheric change alters day length. Every system touches every other system, and the perturbations we are introducing at the surface propagate through all of those connections in ways that are not fully captured in any single model or any single scientific discipline. And the human fingerprint is real, and it is deep. Deeper than most people imagine, deeper than the surface ecology and the atmospheric chemistry and the ocean acidification that dominate public discussion of environmental impact. We have left our mark on the rotation of this planet, on the direction it points, on the dynamics of its crust. We are beginning to leave our mark on the volcanic and seismic systems of the upper mantle. What should we do with this information? The science does not prescribe policy. It describes reality. But it describes a reality that has some clear implications. The Earth's geophysical systems are not infinitely robust. They are complex and coupled and non-linear, and they have tipping points and thresholds that we cannot always identify before we cross them. The changes we are driving are accelerating, and the geophysical responses to those changes will continue to unfold on timescales that extend far beyond the political cycles in which decisions about energy and land and water use are made. The record short day of June 29, 2022 is not, in itself, a disaster. It is a data point. But it is a data point that forced scientists to look more carefully at what is happening inside and on the surface of this planet, and what they found when they looked more carefully is the story we have been telling in this video. A story about a planet in motion, a planet responding to us, a planet whose every layer is connected to every other layer, and whose deepest machinery is engaged with changes that began at the surface, in the atmosphere, in the chemistry of gases that a species of primates started burning in large quantities a few centuries ago. We are not passive inhabitants of this planet. We are, at this point, a geological force, one of the primary drivers of change in a system that has been running for 4.5 billion years. The question of what we do with that force, whether we wield it carefully and intentionally, or continue to wield it accidentally and at escalating scale, is not a scientific question. It is a human one. It is the question of this century and possibly of all the centuries to come. The Earth is not wrong exactly. It is responding. It is adjusting. It is doing what coupled physical systems do when they are perturbed, redistributing, rebalancing, shifting its parameters in directions that accommodate the changes being imposed on it. The question is whether we will be paying attention when those adjustments produce consequences that are harder to absorb than a 1.59 millisecond deviation in the length of a day, because the Earth will keep adjusting, it will keep responding. It has been doing that for 4.5 billion years through extinctions and impacts and volcanic winters and ice ages, and it will continue doing it long after whatever choices we make in the next few decades have played out. The variable in this equation is not the planet. It is us. Thanks for watching.